Quantization of energy. In everyday experience, we observe energy being transferred gradually. For example, when we heat a pot of water, the temperature rises continuously until it boils. Similarly, when we heat a metal, it starts to glow. First red, then orange, and eventually white, indicating that it is emitting radiation. The color of the emitted light depends on its frequency. And this shift with temperature is related to the distribution of energy across different wavelengths. Classical physics, particularly the Rayleigh-Jeans law, attempted to explain this behavior, but failed at high frequencies, predicting an infinite amount of energy, a contradiction known as the ultraviolet catastrophe. According to Rayleigh and Jeans' formula, the problem is that at low frequencies, this formula agrees well with experiment. At high frequencies, especially in the ultraviolet range, it predicts that an object would emit infinite energy, a physical impossibility. This contradiction became known as the ultraviolet catastrophe. Planck solved the ultraviolet catastrophe, starting from statistical mechanics using Boltzmann distribution. This describes the average energy E sub n per oscillator at thermal equilibrium T is given by the probability P sub n. Z is the partition function, also known as normalization factor. Here we see that E sub n is the energy per oscillator and is equal to NHF. We calculate for the average energy per oscillator E. We can use the fact that we let X to be. We see that A sets the scale at which quantum effects become important. It tells us the smallest chunk of energy that can be exchanged at frequency, F. It revolutionized physics by showing that energy is quantized, not continuous.